Right, this lesson is all about bond enthalpies, or bond energies, actually, I should say. Enthalpy change and energy change are largely the same thing. The only difference, enthalpy change, is the energy change per mole, so how much energy is released or taken in, for depending on how much of a substance you have. So if you see the word enthalpy, essentially it's the same as energy. If energy increases, so does enthalpy. So what we are going to be looking at is where the energy comes from in a reaction, or where it goes. So we spoke about how an exothermic reaction is releasing energy to the surroundings, and an endothermic reaction is taking energy in from the surroundings. But where does that energy come from, or where does it go in these reactions? So before we get into that, one of the skills you need to recap from topic 2 is dot and cross diagrams, because fundamentally what we're going to be talking about is the breaking of bonds and the forming of bonds, and they will always use covalent molecules in the examples. So, if we could do covalent dot and cross diagrams, we can identify what bonds are going to be present. Are we going to have single bonds? Are we going to have double bonds? So, again, revisiting topic 2 is really, really helpful for this. So just to recap, even though, I've told you these are covalent, but you should be able to identify that very quickly and easily by looking at the formulas. H2O, they are two nonmetals. They're going to form covalently bonded molecules. CH4, all nonmetals, covalent bonding. CO2, covalent bonding. So we'll start with water. Now, the trick to this is to look at the elements you have, look at what group they are in the periodic table, and use that to determine how many electrons they need to fill their outer shell. So hydrogen is in group 1 because it only has one electron in the outer shell. And because it only has one shell, the maximum of that is 2. So if it's already got 1, it only needs 1 more, which tells you that the hydrogen needs 1 pair of electrons. So 1 single covalent bond. The oxygen is in group 6, so it needs 2 more to fill its outer shell because it wants 8 in total. So the oxygen needs 2 pairs, so it would need to form 2 covalent bonds. So when drawing your dot and cross diagram, you put the atom that needs the most in the center. So I'm going to put my oxygen in the center, my hydrogens either side, and then you start giving them the pairs of electrons they need. So I'm going to start with the hydrogen because it needs the fewest. So I'm going to give that hydrogen 1 pair. I'm going to give this hydrogen 1 pair. And you'll notice that that has now given my oxygen 2 pairs, which is what it wanted. So once you've done that, you just got to make sure you've got the total number of electrons correct. So I'm just going to colour that in a little bit. So hydrogen only had 1 electron and it's used it in the bond. This hydrogen had 1 electron, it used it in the bond. The oxygen, because it's in group 6, had 6. It's only used 2, so it's going to have 1, 2, 3, 4 left over. So in terms of, that's the dot and cross diagram, but as a displayed formula, we can represent these covalent bonds with lines. So we've got a hydrogen with a single bond to an oxygen, which also has a single bond to another hydrogen. There's our displayed formula. And we can very clearly see that in water, we've got 2 bonds, 2 oxygen-hydrogen bonds. So methane, okay, we already know that hydrogen needs 1 pair. Carbon is in group 4, so we'll need 4 pairs. So again, we're going to start with the element that needs the most, put that in the center. So that's our carbon, with 4 hydrogens around the outside. And again, to start giving them the pairs that they need, the hydrogens need the fewest, so we're going to start with the hydrogens. I'm going to give each hydrogen 1 pair of electrons. And again, what you'll notice by doing that, the carbon now has 1, 2, 3, 4, which again is what we said it would need. The hydrogen had 1 electron to start with, and it's used that in the bond. And the carbon had 4 electrons to start with, and it's used all 4. So that's it. We don't have to add any extra electrons. And in terms of the displayed formula, we can replace each one of these covalent bonds with a line. So carbon with 4 hydrogens. And again, now we've done this, we can see that this molecule contains 4 carbon-hydrogen bonds. Right, carbon dioxide. So again, we've already done this, so we know carbon needs 4, we know oxygen needs 2. So the carbon needs the most, so that's going to go in the center. And we're going to have our oxygens on either side. And we're going to start with the oxygen because the oxygen needs the fewest number of electrons, but it doesn't need 1, it needs 2. So we're going to give each oxygen 2 pairs. So 2 crosses, 2 dots. And again, look at the carbon. The carbon now has 1, 2, 3, 4. So looking back at the atoms, the carbon had 4 to start with. It's used 1, 2, 3, 4, so it has none spare. The oxygen was in group 6, so it had 6 to start with, and it's used 2, so it still has 4 electrons it hasn't used. So in terms of drawing this one as the displayed formula, these are not single bonds, they're double bonds because they have 2 pairs. So we're going to draw it as 2 lines rather than 1. And then finally, oxygen O2. So we know that it needs 2 pairs of electrons. So we're going to have 2 oxygen atoms. Both need 2 pairs, so they're going to have a double bond in between them. They both are in group 6. So they've used 2, they've got 4 left. So 1, 2, 3, 4, 1, 2, 3, 4. And then we're going to draw that like that. So again, this was just a recap of topic 2, but being able to get these formulas, these displayed formulas, is going to be really useful for when we're working out bond energy calculations. So fundamentally, what's happening, in order to get from reactants to products, what we need to do is break the bonds in our reactants and then form new bonds in our products. Okay, so if we add some example to this, I don't know, if we have methane reacting with oxygen to form carbon dioxide and water, and if we balance it, we'd need 2 water molecules and we'd need 2 oxygen molecules. So you'll notice in a balanced equation, you've got the same number of atoms on both sides, haven't we? We haven't lost or gained any carbons, we haven't lost or gained any hydrogens, we haven't lost or gained any oxygens. We have the exact same number of both at the beginning of the reaction and at the end of the reaction. The difference is they've got different bonds. So in order to rearrange them, in order for them to become carbon dioxide with these new bonds or water with these new bonds, we need to first break these original bonds. Okay, so breaking bonds requires energy, and a reaction that requires energy is endothermic. So breaking the bonds in our reactants is an endothermic process. Forming new bonds, however, gives off energy, and it's exothermic. So our overall energy change is determined by how large these two values are. If they're the exact same, so let's say that it took 500 kilojoules to break the bonds, but then it gave off 500 kilojoules making new bonds, then the overall would be 0. There'd be no energy change. But if one of these was larger than the other, then you would have an overall energy change. If, for example, it took 1,000 kilojoules to break the bonds, but it only gave off 500 when it formed new ones, then it would have a 500 kilojoule deficit. It would need to take 500 kilojoules from somewhere else, and it would be endothermic. And vice versa, if the exothermic value was higher than the endothermic value, so let's say again, if the products gave off 1,000 kilojoules of energy, but it only took 500 to break the reactants, we'd have an excess of 500 kilojoules, which would be released to the surroundings. So this is the equation. The overall energy change is the sum, this little symbol here, it's a mathematical symbol for sum. So the total bond energy of the reactants subtract the total bond energy of the products. So the two bits of information we need, number one, we need to know which bonds do we have and how many of them do we have in our reactants and our products. But importantly, how much energy is required to break them. Okay? Now, you are not expected to remember that. You will be told the energy of the bonds. You've just got to be able to work out which bonds do you have and how many of them do you have, and then substitute in the values given. So if we turn the page, so again, this symbol here, that's the symbol for enthalpy change. And again, we said right at the beginning that that is the same as saying energy change. Okay, so it's the same as delta E, which is energy change. So don't be thrown if you see the word enthalpy. It's the exact same thing as far as you're concerned. So energy change or enthalpy change is the difference between the energy needed to break the bonds in the reactants and the energy given out when new bonds are formed in the product. And this might seem simple and straightforward, but it's really important that when you're talking about the bonds in the reactants, you are saying that they are being broken. But when we're talking about the bonds in the products, they are being formed. Because there will be questions that ask you to explain why is a reaction exo or endothermic. And if you start talking about breaking bonds in the products, you're going to lose the marks. So it's breaking bonds in the reactants, but forming bonds in the products. So in a question, they will give you a table like this, which has the values of these bonds, how much energy is required to break these bonds. Okay, and you'll notice that double bonds require more energy, and that makes sense, doesn't it? Because they're stronger. So write a word equation for methane when it reacts with oxygen to form carbon dioxide and water. Well, that's nice and straightforward. Methane plus oxygen goes to carbon dioxide and water. Write it as a balanced symbol equation. Okay, so we've got methane, CH4, oxygen, forming CO2 and H2O. So in order to balance it, I've got one carbon here, so I must need one CO2. I've got 4 hydrogens here, so I'm going to need 2 H2O, and that's going to give me 1, 2, 3, 4 oxygens, so I need 2 O2 to balance that. So it says draw each of the molecules in the balanced equation showing their bond. So this is where what we did on the other page is going to come in useful, because we need to be able to see how many bonds and what bonds are in these compounds, and it's much easier to do that if you draw them out. Okay, so we've got methane, CH4. We've got 2 lots of oxygen, so I'm going to put that in brackets. So I've got 2 lots of this molecule. I've got carbon dioxide, and again I've got 2 lots of water. Okay, I'm going to put it in brackets. So I've got 2 lots of this molecule. So this example is broken down for you. It won't be like this in the exam. You're going to have to sort of structure it yourself. So use the bond energy data to calculate the amount of energy required to break all of the bonds in the reactants. So how many CH bonds do we have? We've got 1, 2, 3, 4. Okay, so the energy of that bond, you are told in the table up here, you're told it's 413 kilojoules. So in order to break all 4 of them, it's going to be 4 lots of 413 kilojoules, which is 1,652. How many oxygen double bond oxygens do you have? Well, you have 1 in the molecule, but you've got 2 molecules, so we've got 2 in total. And they have a value of 496 again, which is in the table above. So 496 times 2, 992. So the total energy is going to be those 2 numbers added together. 2644. So that is the energy to break bonds in our reactants. Now we need to work out how much energy is in the bonds of our products. So again, carbon double bond oxygens. So we've got 1, 2 of those. And they have a value of 743 kilojoules. So 2 times 743, 1486. And number of oxygen-hydrogen bonds. Well, we have 1, 2 in the molecule, but we've got 2 lots of the molecule, so we've got 4 in total. And they have a value of 463. So 1852. And again, we're going to add those together. Three, 3, 3, 8. And straight away, before I've done the calculation, I can tell that this reaction is going to be exothermic, because the amount of energy that's going to be released when I break the when I form the bonds in the products is significantly higher than the energy taken in to break the bonds in the reactants. So I can already see there's an imbalance, and that the energy of the products, the energy that's going to be released, when I form the bonds in the products, is going to be much higher than the energy taken in breaking the bonds in the reactants. So again, turning the page. So it says now calculate the overall energy change for the reaction. So we need the energy of the reactants, which was 2644, minus the energy of the products, which was 3338, giving us a total energy change of negative 694. Okay, and the fact that it's negative tells us that it's exothermic. And another thing we can look at is this whole thing was a combustion reaction, and we know, or should know, that combustion reactions are exothermic reactions. So finally, produce a fully labeled reaction profile diagram for the reaction above, making sure you include the following. Okay, so we're going to use that information to annotate this diagram here. So again, the first thing you should do is extend both of these lines, your reactants and your products. And remember, your energy change is going to be going down from reactants to products. So there is my change in energy. It's going down, so it's going to be a negative change. And my activation energy goes from the reactants to the top of that curve there. And that there is my activation energy. And finally, describe and explain why the line rises and then falls to a lower level. Okay, it rises because that's the energy needed for the reactants to actually collide successfully. Okay, so it rises for the activation energy needed for reactants to collide successfully and actually react. It falls because the products are at a lower energy than reactants. Energy is transferred to the surroundings. Because the reaction is exothermic. 4 points, 4 marks.